I work here as a meteorologist, and Polish Polar Station will be my home for at least the next few months till July 2018. And today I would like to say a few words about Northern Lights, about this magic spectacle in the sky that we can see here and not only here. So let's start. People have wondered for centuries, what is it? What are these magical lights that they could see in the, for example, ancient China or even ancient Greece? There were a lot of ideas what that could be, depending on the place where people could observe it. For example, in ancient China, people thought that it could be the dragon's breath when they saw the red lights in the sky. In Norway, it was believed that it is light reflected by giant shoals of herrings, which is herrings are a classic Norway thing. On the other hand, in Greenland, it was believed that the lights in the sky are the souls of people that passed away recently. Something similar was believed in, for example, Scotland, because people believed the lights were ghosts of dancers, so they were calling it the merry dancers, because as the lights changed, they believed that they are dancing in the sky. Some tribes in Northern America thought the lights could be a sign of incoming war or a disease. In Finland, it was believed that the aurora was formed by a magical fox sweeping his tail across the snow, spraying it up into the sky, and that's how the snow changed into colors. So, as you can see, there are a lot of myths, legends, and beliefs connected with aurora, but nowadays we know that aurora is not ghost, but a light phenomenon. A light phenomenon occurring in the upper layers of our atmosphere. This phenomenon is caused by the collisions of charged plasma particles with gas molecules in the Earth's atmosphere. This might sound a little bit difficult, but we will get through that. This phenomenon, aurora, occurs in the thermosphere, which is part of our atmosphere, at the altitude of around 100 to 200 kilometers, so quite high. And the official name that we are using nowadays, so aurora borealis, was given in the 17th century by French astronomer Pierre Gassendi. Okay, so how actually aurora is formed? So everything starts on our sun, our active star, that is constantly emitting a stream of charged particles, electrically charged particles, that is important. This stream of particles is called the solar wind, and it consists mostly of electrons and protons that are in a form of a cloud of a hot ionized gas, which is known as plasma. So solar wind is more or less plasma. Another important thing for aurora is the solar activity. The solar activity manifests itself in a form, among many other things, but mostly in a form of coronal mass ejections and flares. And a photo of a flare you can see on the right side of the slide. This was made by the Hubble telescope. So the solar activity. And from the over 200 years of observations of the sun, now we know that the solar activity changes in time, and it's cyclic. One solar cycle, as you can see on the slide, lasts around 11 years, and it starts when the sun is, well, let's say calm, when the solar activity of the sun is in its minimum, as you can see on the picture. This solar activity is also measured by, for example, number of sunspots, as on this picture here. So the cycle starts when the sun is in its minimum, then it rises to the maximum, which is this characteristic period in each cycle, and again decreases to another minimum. As for observing aurora, the most important thing is this period when the sun is in its maximum, because on that time we've got a lot of flares, a lot of coronal mass ejections, average 3 per day, so that's quite a lot. And both these ejections and flares influence the strength of the solar wind. By influence, I mean that it increases the strength of this solar wind. And if this wind is stronger, then we have a bigger chance to see aurora on Earth. So for us, the maximum of the solar activity is the most important in case of aurora. As you can see also on the picture, at the moment we are approaching to the end of the 24th solar cycle. So we are getting to the minimum of the activity, but that does not mean that nothing is happening, right? We also have coronal mass ejections, but simply not as much as during the maximum, because now it is on average, let's say, 1 in 5 days. Not much, but still something is happening. So let's get back to how the sun contributes to the formation of the aurora. So as I already told you, sun emits the solar wind, and the solar wind moves with an average speed of 300 to even 1,000 kilometers per second, so really fast. It takes around 2 or 3 days to travel from the sun to the Earth. And what is important is that when the solar wind reaches to our planet, it meets with our magnetic field, with the Earth magnetic field, so-called the magnetosphere. And the magnetosphere is protecting us from the harmful solar radiation. That's one of the reasons why we can live on our planet. So solar wind encounters magnetosphere, and when it happens, the solar wind presses magnetosphere, so it bends, and it is deformed, and the magnetosphere bends the solar wind towards the space, the cosmic space. So, to say colloquially, we could say that our magnetosphere works a little bit like an umbrella that is protecting us from this solar wind. The picture, I think it's quite clear, but I would like to show you a small animation of how it actually is. This magnetosphere is deformed by the solar wind. I hope you will be able to see it. I just need to switch. Okay, I hope you can see it now. I will just play it. So you can see how the solar wind is striking and how our magnetosphere is deformed. So it bends and the solar wind passes beyond our planet. But if you will take a closer look, some of this red color gets somehow near our planet. And that will be important for what I will be telling you next. So let's get back to our presentation. Yes, so as I said, magnetosphere works a little bit as an umbrella, but it does not protect us completely. As you saw on the animation, and as you can see on the picture on the right, some small number of these solar particles actually enter our magnetosphere. So they penetrate it and they can reach our atmosphere. When this happens, when those solar particles actually get into our magnetosphere, they start to follow the lines of our magnetic field. The schematic diagram of this you can see on the left, how it looks like. So those particles travel along these magnetic lines to place where this magnetic attraction is the strongest. And that's why we can see aurora only in some certain places on the Earth. And those places are called the aurora ovals. It's a region where it's a region in a shape of a ring, let's say, that is surrounding our magnetic poles. As you know for sure, Earth has two magnetic poles, just as we have two geographic poles. But what is important that those poles are not exactly in the same planes. So magnetic poles are slightly moved regarding the geographical poles of the Earth. So you can imagine that we will have aurora both on the northern hemisphere and southern hemisphere. On the northern hemisphere, the highest probability of seeing aurora is between 60 and 70 degrees of northern latitude. You can see it in the places like Alaska, northern Canada, southern Greenland, Iceland, northern Scandinavia, or northern Siberia. And as you can see on the picture on the right, average percentage of nights with aurora in these regions is approximately 80%, even up to 100%. It is said that during high solar activity, we can, in such places like I just mentioned, we can have up to 240 nights with aurora per year. So really quite a lot. In northern hemisphere, the official name for aurora is aurora borealis, and in southern hemisphere, the official name is aurora australis. And as to where you can see it, that's mostly Antarctic in the south. But if the aurora is quite strong, this aurora oval may change its width, and you could see the aurora even from Australia. So that's possible. Okay, so I already told you how aurora is formed, but what is responsible for the color of it? Because as you may know, aurora can have different colors. As I already said, aurora is an effect of collision of solar wind particles with gases in our atmosphere. So the colors will depend from, first of all, the type of an atom with which the solar particle will collide, of the impact speed of that collision, and from it will depend also on the altitude at which this collision will occur. As you know, our atmosphere consists mostly of nitrogen and oxygen. So those two gases will determine the colors of the aurora. Well, gases and their properties, right? So how does it work? Above around 120 kilometers, our atmosphere is dominated by atoms of oxygen. Atoms of oxygen can emit mostly green and red light. But as maybe you know already, or you will have a chance to see, the most common color of aurora is green. Why is that? That's because at the altitude of, like I said, around 120 kilometers, our atmosphere is far more thick. It's more dense than at the altitude of 200 kilometers. That's why a collision between the solar wind particles and oxygen atoms is far more possible at this lower altitude. So it is more possible, the collision is more possible at 120 kilometers than at the height of 200 kilometers. That's why we see red auroras, well, not very often. That's why we mostly see it in the green colors. On the other hand, below the 120 kilometers, atmosphere is dominated by nitrogen particles, which gives us the colors of violet and blue. But that's also not as often as this green color. And we can see those colors in the sky in general, because during a collision of solar wind particles with, let's for example, these oxygen atoms, solar wind particles transmit their energy into those atoms, and oxygen atoms or nitrogen particles or particles of other gases, they want to return to their initial state, and they do that by emitting this energy in the form of a light. So colloquially speaking, they shine, and that's why we can see aurora in the sky during the night. Okay, so now something for those who would like to become aurora hunters. Can we predict aurora? Well, nowadays definitely we can. A very helpful thing in aurora hunting will be KP index, which is a planetary index, which quantifies disturbances in the Earth's magnetic field. It can have values from 0 to 9, where 0 means that these disturbances in the magnetic field are very small and nothing important is happening. While when this planetary index is 9, that means very big disturbances in the magnetic field, very big distortions. And also, it is good to know that if this KP index is equal to 5 or it's higher, then we are talking about magnetic storms. So it works like this. If you have KP equal to 5, then you have a magnetic storm equal to G1, because magnetic storms are also classified from G1 to G5, well, where G5 is this super strong magnetic storm. Another thing is how it works. So the more solar wind is in our magnetosphere, the more of this solar particles gets into our magnetosphere, the higher will be this Kp index, and a larger area will be where we can see the aurora. So the higher Kp index, there is a bigger chance of seeing aurora all around the world. And another thing that might be worth knowing is that this Kp index is a 3-hour average that is calculated from K indices from a network of geomagnetic observatories all around the world within the Intermagnet network. And you can see on the picture stations that are within this network. And as a matter of fact, Polish Polar Station is also one of the sites that where those measurements are made. We are here, as you can see. And that also means that you can check the data from our station in the internet. This is, for example, a part of the magnetogram from this September. So you can check online how it looks on our station, on any other station probably near you. On the picture, you can also see my friend, our geophysicist, during the measurements that are also needed to make some corrections in these magnetograms. So thanks to that kind of measurements that are made also here in Hornsund, and a lot of observations, you can find in the internet, for example, also some sort of maps or diagrams where you can check with what Kp index where you can see the aurora. As you can see, the stronger is the higher is this index. The far to the south, you can see the aurora. So, in case of Poland or let's say Germany, to see the aurora, you have to have this Kp index at least at the level of 7. So it has to be a magnetic storm class G3, because otherwise it is, well, not possible. This aurora oval won't reach as far as to those countries. That does not happen very often to see aurora in places like Poland, Germany, or northern France. But for example, in September, we had a heavy magnetic storm, class G4, and maybe even you in your countries could see the aurora. I know that in Poland, a lot of people could see it, and there were a lot of really beautiful pictures from that time. Another thing that might be helpful in aurora hunting are the mathematical models that are made these days. You can see on the slide aurora forecast made by NOAA, Space Weather Center. So these models can show you with where, when, and with what probability you can see the aurora, both in the north and in the south. So I think that's pretty useful if you have a chance to be somewhere in the north or in the south and to hunt for the aurora. So you can find many of such models in the internet. There are many websites that visualize that kind of things. So that's helpful. Okay. Another question that you may ask yourself is whether aurora can somehow influence us and our world. Well, what can I tell? As a phenomenon itself, aurora does nothing. At least we don't have any scientific proof that it is somehow influencing us. But the phenomena that are um, creating the aurora, well, especially I mean the magnetic storms, actually can influence the world. Maybe not human body, our organism, but let's say the technical aspects of the world. Because during a heavy magnetic storm, quite a lot of things can happen. Magnetic disturbances can cause, first of all, radio interference. So you may have problems with radio communications. It can be totally dead for some time. But what might be even shocking, that kind of magnetic disturbances can destroy the infrastructure on the ground, mainly power grids, because as I told you at the beginning, solar wind is a stream of electrically charged particles. So power grids doesn't like that kind of things. Also, if you're using GPS systems, they might work not as they should. They might not work at all, or they might show you incorrect data. And magnetic storms can even change satellite trajectories. So this influence actually might be quite big. And one of the examples of magnetic storms is one that occurred in 1859. It is called one of the biggest storms in our history, one of the biggest magnetic storms. And one of the signs that it was a really huge storm was the time in which the solar wind reached the Earth, because, as I told you at the beginning, it takes around 2 or 3 days to get to Earth. But in 1859, it took it 18 hours. So that was really, really fast. And what were the consequences of that storm? First of all, a giant failure of telegraph networks around whole Europe and North America. Everything was so charged with electricity that even when you plugged off the telegraph, you could still send telegrams. So you can imagine how unnatural that was. And aurora was so strong that you could see it even in the Caribbean. So imagine how far from the north is that. And what else I can tell you is that that kind of very strong magnetic storms occur on average every 500 years. How do we know that? We know that because of the ice core analysis from the places like Arctica or Antarctica, because during a magnetic storm, a lot of nitrogen compounds is being created. And if you analyze the ice core regarding those quantities of nitrogen compounds, you can tell that that kind of storms were happening in the past, and they occur on average every 500 years. The question is, can we hear aurora? Well, not directly, but when aurora is occurring, sometimes there are electromagnetic interference that can be heard when you use some simple receiver, simple device. Another question: is aurora characteristic only for the Earth? Well, no, it's not. As you can see on the picture, that's a photo of Jupiter with a beautiful blue aurora. So aurora can occur on all planets that have strong bipolar magnetic fields. So it is not typical only for the Earth. It can occur on all of the planets with this strong bipolar magnetic field, like Jupiter, like Saturn, Neptune, and so on. So if we will be able to travel to Jupiter one day, we can look at wonderful blue aurora there. And this is a picture from outside my window here at the station. Well, at the moment, it doesn't look like this because we still have some daytime. The polar night will start in a week or two. But when the night is outside our windows, the sky can look like this when there are no clouds, of course, because when you have clouds, you won't be able to see even the strongest aurora, unfortunately. So clouds are not good. And here is the picture of the aurora above our main entrance to the station. Well, quite beautiful, I would say. But yes, on the pictures, aurora is of course beautiful in my opinion. But is it a static phenomenon now? Well, I would like to answer you that question with showing you a small video. So I hope you can see that it is not static at all. It can change really, really fast. And I must say it is quite fascinating to watch it. You can stare into the sky, well, sometimes for hours and sometimes just for a few minutes because aurora can last as well, very short as also very, very long. And another video. This is short, so I will just leave it. So as you could see, aurora is not a static phenomenon at all. It can be really dynamic, and well, it's beautiful. But another question is it disturbing our work here at the polar station? When well, you can imagine, I think, that after all that I told you, that when aurora is showing on the sky, that means also that these geomagnetic disturbances are present. So it is a problem for us here for our work, mostly because we might have problems with radio communication, which is our main source of communication when we are in the field. Because as you know, we don't have any cell phones here because we we don't have the range to use it. Cell phones don't don't work here. So when, for example, our land surveyor goes to the glacier to make some measurements, he might not be able to contact with us. So that's important. If any emergency will happen, if anything happens, anything bad, if he would need help, he might not be able to contact us. So that's a big problem. Just as if we want to warn somebody that we saw just a polar bear that was going towards some of our expedition members. So yeah, that might be a big problem. Also, it's a problem during our measurements. For example, the geodesic measurements, because we are using GPS systems. So during a big magnetic storm, we actually are unable to make any of those measurements because we will simply get a lot of incorrect data. Just as with the geomagnetic measurements, our geophysicists can't do those measurements during big magnetic storms because it has no sense. And maybe something that will sound quite funny, but also during aurora we might have problems with the internet. Well, in general, we don't need that. We can live without it, but that's important for the data that we're sending to some institutions, to some other measurement networks such as NASA. So we cannot send those data during a heavy magnetic storm because of those problems. So that's the sign just outside our main entrance. And another thing that I wanted to tell you, something interesting in my opinion, but a human can also trigger the aurora. Human history knows two such exceptions. Once it was happened by detonating a nuclear charge that was hitting the ionosphere, and that's how the aurora was formed. So it was induced by human. And one thing to remember, if you want to watch aurora, aurora can last 24 hours a day, but you will be only able to see it during the night. So the best places to see it are somewhere far beyond cities. Well, generally somewhere where there will be no source of artificial light. And remember about the clouds. If there are clouds, even if there is a super strong aurora, you won't be able to see it, unfortunately. Okay, so you listened to me for some time. Now I can listen to you. Do you have any questions about the aurora or anything else, the station or what we do here? So please feel free to ask.